Hello everyone, my name is Ning. I'm from the University of Alberta. Today, I'm excited to share our work on lexical substitution as causal language modeling. This is teamwork with Dr. Bradley Hauer and Professor Greg Kondrak. Our research was supported by Insert and Amy. Let's start from what we focused on, the lexical substitution task, LST. The objective of LST is to identify an appropriate replacement for a target word within a sentence while preserving its contextual meaning. Here is how it works. You take a sentence and pick a target word to replace, then you list the potential word that could fit there. For example, in the sentence, "Let me begin again." If we want to replace begin, options could be start, commence, or open. It is important to keep the target word in mind and also think about its attributes, such as parts of speech. Here, begin is a verb. If we forget this and put begin again together, then we might confuse it with the title of the American musical comedy movie called Begin Again. Without more context, the meaning of the target word begin can be even more confusing, which might actually stand for a new start to a relationship in the movie. From our literature review, we found some limitations in existing methods. A common issue is that the predicted substitute could fit the context, but might change the original sentence meaning. Let's look at method based on masked language modeling. When we mask the word begin and consider substitutes like start in sentence 1 or originate in sentence 2, both can grammatically fit the context within the sentence. However, start is preferred because both start and begin as verbs, meaning taking the first step in action. On the right-hand side, originate means bring into being, like originate a foundation. Also, most methods are pipeline approaches depending on manually defined heuristics, extensive processing steps, and external resources. Moreover, there's a notable gap in previous supervised methods between the pre-training task of language modeling and the fine-tuning task of lexical substitution. In response to these limitations, we introduce our work as the first single-step, end-to-end generative solution for LST. Our approach successfully reduced LST to causal language modeling via formally defined task reduction. Also, our method achieved overall state-of-the-art result in the comparison with previous methods. Finally, we demonstrate the scalability of our approach through extended data resources, increased model capacity, and the use of retrieval augmented generation, RAG. Our method builds upon two binary problems, lexical substitution and word prediction. Lexsub is to determine if word Y can replace word X in a sentence S without altering its meaning. For example, in the sentence, "Let me begin again," with begin and start as two provided words, Lexsub would return true. Word prediction is to detect whether a given word has the same meaning of a masked word in a sentence. Using the same example, with begin being masked and the start is the provided word, word prediction would return true. Putting these two binary problems together, we can achieve the task reduction from Lexsub to word prediction, which is the basis of our method. A P2Q task reduction is to solve an instance of a problem P by combining the solutions of one or more instances of Q. Taking Lexsub as the P and the word prediction as the Q, we can achieve the task reduction that if both the word X and the word Y have the same meaning as the masked word in a sentence, then the word X can be replaced by the word Y in the same sentence as without altering its meaning. Given the defined task reduction, we implement our method to calculate the probability over the vocabulary for word prediction. By putting our context to the left side of the masked word, we can model Lexsub and the word prediction through autoregressive language modeling. This allows us to introduce our PromptSub, a novel method for lexical substitution via prompt-aware fine-tuning. For example, using InfoPrompt, we incorporate additional attributes of the target word into the context, including its lemma form, post tag, and position. This information exclusively comes from the LST data, but were ignored by the previous method. As shown in the figure, we can verbalize the raw LST instance into a description that positions all the useful contextual information to the left side of the substitute. We further alleviate the frequency information associated with each gold substitute by feeding them into a softmax function, thus enabling the use of weighted sampling in our verbalization process. We compare our prompt sub against the previous top-performing supervised method, Genesis, using the same evaluation protocol on LS07. We also include an enhanced version of Genesis that incorporates WordNet to refine its output. To verify the scalability through data resources, we also introduce Prompt Sub Plus, which augments the training set by including depth set. The two-bar chart demonstrates that our Prompt Sub outperforms Genesis in all the settings and evaluation metrics. With data augmentation, the performance of our method can be further improved. While evaluating our prompt sub on the more recent LS21, prompt sub continues to lead significantly, especially regarding the conceivable F10 score as shown in subfigure B on the right-hand side. This includes outperforming the previous state-of-the-art method, PyRLS, and its variant. It should be pointed out that our prompt sub takes GPT-2 medium as its backbone, which is generally considered less powerful than GPT-3 and the BART large used by Genesis. Given that, we have a good reason to speculate that with full access to GPT-3 or even GPT-4, our method prompt sub could produce even stronger results. In terms of scalability of our prompt sub, we provide a best practice with retrieval augmented generation, RAG. Specifically, EXPrompt retrievals WordNet scene set to enrich the context information in the prompt template. We can see from the first line chart that EXPrompt can lead to lower loss, higher top point precision, and faster convergence. Also, the second line chart confirms that models with larger capacity can achieve better performance in fewer training epochs, showing the benefit of scaling up model size. In conclusion, we have presented prompt sub, applying causal language modeling to the lexical substitution task through a formally defined task reduction. Our method bridges the gap between pre-training and fine-tuning, takes advantage of larger model capacity, alleviates extensive data resources, and benefit from external knowledge, for example, using RAG. In future, we plan to extend our method to the other semantics tasks. So please follow our GitHub repository for our code, data, and more details. That's the end of the presentation. Thank you for your attention.